This video is just an introduction to the process. We're going to take it apart and go through it step by step, but it's an introduction to the process along with some vocabulary that you need to understand in linear programming, and it is also the rubric, so kind of how you're going to be graded on it without the points, because the points will vary per the questions. So the first thing that you do when you get a linear programming problem is you have to read the problem, and then you have to pick out the constraints, the boundaries, which are the inequality equations. You have to write your objective function, which is always in your question, and it's the maximum or the minimum, and it's important that you write that down because it depends on which it is as to how big of a number you're looking for or how small of a number. To show your work with writing the constraints, I'm going to ask you to create a table with the information given and identify your variables. So like in the example, X was the number of spruce trees and Y was the number of maple trees. The second part, which is part of the meets, the expectations of the standards, is the feasibility and boundaries. So you're going to graph the constraints and identify the critical points, and you're going to use Desmus to graph them. I'm going to give you a link to Desmus, and I'm going to show you how to use Desmus. You just really type in the equations, and it takes care of it for you. And then you have to identify the critical points. So you're going to see the feasible region, which we're going to talk about in this video, and then what the critical points are, because you use those critical points for your solution. So, and then number 3 is the solution. You have to identify the mathematical solution by using the critical points and writing the solution to the question asked in the word problem. To start, the word constraints and the objective function. A system of inequalities, so that's more than one inequality, is used when a problem imposes multiple conditions. So there's like the amount of land that you can use, the amount of money that you can spend buying it in the plant problem. Or it's called the constraints, and they are inequalities. To be considered simultaneously, which means at the same time, each constraint is modeled by an inequality. So the constraints that we had in the tree growing problem was that X is greater than or equal to 0, because you're never going to have a negative planting of number of trees. Y is greater than or equal to 0, and then 30X plus 40Y was less than or equal to $2,100, because we had $2,100 to spend, and the maple trees, or the spruce trees, cost $30, and the maple trees cost $40 a piece. And then the amount of land that it took up was in square feet, so there was 600 square feet that was taken up for the spruce trees, and 900 square feet that was taken up for the maple trees. And then we couldn't go over 454,000 feet squared, because that's the amount of land that they had available. The objective function is a statement that is to be optimized. Optimized means makes the maximum or the minimum. You identify the vertices that result in the maximum or minimum value of this function. But first you have to write the objective function, and the objective function is always in the question. It will say maximum or minimize. And then you write an expression. There's no equal sign in it, because you're going to find out what it equals when you plug in the X and the Y. Oops. Okay, the process and the rubric. The process, this is the first part of the process, is the constraints and the inequality and the objective function being written. Now, This is so that you so that you don't just meet, that you exceed the expectations. So you can pass the lesson by not doing this part. You can be given the constraints. And so you're going to have 2 problems to do for your assessment, and one of them you're given the constraints, and it gives you enough points to pass the lesson. And the other one, you have to find the constraints and the objective function, and that's so that you can get a higher percentage. You're exceeding the expectations. So to show your work, we create a table with the information given, and then we identify the variables. So the rubric part for this is the problem understanding. You can write the constraints, inequalities, and the objective function, the max or the min. So we're going to concentrate on the exemplary piece, because the rest of it is where the errors are made. Okay? So clearly understands the problem, defines the variables, the constraints, and an objective function and their meaning explicitly. Okay? So then, okay, when you graph the constraints, you're going to be doing this on Desmos, but when you graph the constraints, you're graphing inequalities. And in the previous section, you graphed inequalities, and you saw that you had to shade regions. Well, the region, the area, that is shaded by all of the constraints that you're putting in. So where it crosses over with the shading is your feasible region. So right here, the feasible region goes from here to here to, oops, I went ahead, to here, to here. So it's kind of this triangle, but it's kind of cut off here, so it is a quadrilateral instead. Okay, a system of linear inequalities creates a feasible region. That's where your possibilities exist, of possible or feasible solutions. The intersections of the lines bordering this region are the vertices. Not all points of intersection are vertices of the feasible region. So we have our boundary line here, and we have a boundary line here that's blue. We have a boundary line here that's green, and we have a boundary line here that's purple. So the feasible region is this inside part where all of the shading crosses over. And then the critical points are the vertices, so where the intersections are of the feasible region. So this would be a critical point, this is a critical point, this is a critical point, and this is a critical point. Okay? All right. Here's another kind of picture where it points out the critical points. So if you're not seeing my arrow as I'm pointing to it, I think that it turns yellow on it. But the critical points of this feasible region are here, 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 and here. And this is my feasible region. It's the vertices at corners of the feasible region. Okay? Okay, so the feasible region and the critical points has to do with the second step, which is when you graph it on Desmos, and then you pick out the critical points and you can have Desmos label them. And to show me it and also to work towards it when you put it on to your explanation of doing the problem, you want to take a screenshot of it when you're done, and then you'll insert it. So exemplary means that you clearly define the feasible region by identifying all of the critical points correctly. So in the proficient, you might have made a little slightly off on the boundaries, so your critical points aren't all correct. And developing is when you have more errors in your boundary or not identifying your critical points. So critical points in the objective function is really the last part of it, but you need the critical points in order to apply it to the objective function. So this is part of the second process, and then when you take a screenshot and insert it, then you're going to take those critical points and you're going to plug them in, so substitute them in to the objective function to find out whether it's the max or the min. The max, you're looking for the highest number that you get. The min, you're looking for the smallest number that you get. The objective function is a statement that is to be optimized by identifying the vertices that result in the maximum or minimum value of this function. The fundamental theorem of linear programming states that the minimum or maximum value of the objective function occurs at one of the vertices of the feasible region. These vertices are defined as the critical points. The objective function may not always yield a number that fits the context. It may be necessary to adjust the value to be an integer that meets the constraints. So the solution part of solving is identifying the mathematical solution using the critical points, writing the solution to the question asked in the word problem. So this is where we had the largest amount, and the question was, how many of each tree should the city plant to maximize carbon dioxide absorption? So that's what came up with my objective function. And then I plugged it in. I found out that the maximum carbon dioxide absorption is 165,000 pounds per year. And it's obtained by planting 50 maple trees only. So exemplary would be provides a clear and correct interpretation of the optimal solution, including the values of the variables and the objective function. So you want to write it in you want to answer the question from the problem. You don't want to just leave it like this. This doesn't tell the person who's asking the question anything, really, okay? Because it's mathematical. So you're making them figure it out then. All right, I need to wrap this up. So this is the whole rubric. As I said before, you really have to do the last two parts, so you're going to have a rubric for grading the last two parts on one problem, and then all three parts on the other problem so that you have the chance to exceed the expectations.